I'm Sophia, and in the Week 7 lectures, we talked about changes in electric potential, or electric potential energy. So you can store potential energy by bringing a particle close to an electric field. The closer you bring the particle to the electric field, the more potential energy you will store, because you have to put in work to bring this particle close to an electric field. Moving the particle around in the vicinity of an electric field can cause changes in the potential energy stored in the system, i.e. in that particle. Changes in electric potential are path independent. That means that it only matters, or the only things that matter to calculating the change in potential energy is the place where the particle started and the place where the particle finishes. And it doesn't matter what path the particle took to get from the start to the finish. This allows us to pick a path that makes our calculations easier when we're trying to calculate the change in electrical potential. One thing we can make use of is the fact that the dot product of two parallel vectors is just the product of the two vectors' magnitudes, and the dot product of two perpendicular vectors is 0. Therefore, we can split up the path from the initial location to the final location into several components, so that some of these components are perpendicular to the electric field, and some of these components are parallel, so that we can use those simplifications in calculating the dot product. Interestingly, when an electric field emanates from a point charge, the electric field will point radially outward, and so a circular path of constant radius will be perpendicular to the electric field. Finally, we were reminded of how charged spheres with an even distribution of charge behave. These spheres act like point charges if you're outside of the sphere, the sphere emits an electric field like a point charge. However, inside the sphere, the electric field is 0. Or rather, the net electric field is 0. Because my section had actually gotten ahead in lecture the previous week, we had already covered most of this material in class, so it wasn't really new to me. However, watching these videos helped me make more sense of what we were studying and kind of tie the material together. And I was previously in lectures confused about why a path that goes in a circle around a point charge is parallel to the electric field emitted by a point charge, but watching these videos and seeing that illustrated helped me answer that question. So I'm not currently confused about anything else, because I've been asking questions in class throughout the week. But if I'm ever confused about something else, I can ask a question on CampusWire, or go to office hours, or read the student wiki. Although I previously saw a lot of this material in class, watching this material again, especially for the purpose of making this video, made me think about mass spectrometry. And the concepts from this week relate a lot to how electrospray ionization in mass spectrometry works. So I finally took the time to learn about how electrospray ionization works. So mass spectrometry is a technique commonly used in biology research to profile the different kinds of proteins, lipids, or other biological molecules you have in your sample. So droplets of your sample are fed into a vacuum through a capillary that has a difference in electrical potential from one end of the capillary to another. And as the droplets pass through this capillary in the vacuum, the solvent in the droplets evaporates until the droplet becomes unstable and explodes into many smaller droplets, which is called fission. During this fission process, the droplets become ionized. They lose a little bit of their mass and a lot of their charge. So they lose some electrons and they gain a positive charge. And then these positive ions are sent into a quadrupole, which is a stack of 4 electromagnets. And 2 of these electromagnets generate a negative electric field, which basically points inward towards the magnet. And the other two the other two magnets in the quadrupole, they generate a positive electric field which points outward from the magnet. And since the ions in the sample are positively charged, they will be attracted to the electromagnets with a negative electric field and repelled from the electromagnets with a positive electric field. And the electric field of the quadrupole is varied, so that only particles with a particular mass to charge ratio, or ions with a particular mass to charge ratio, can pass through, because the attractive and repulsive forces kind of balance each other out, and the ions, they don't really have an opportunity to crash into the part of the quadrupole with a negative electric field. Now, particles with other mass to charge ratios will become unstable, and they'll smash into the magnets rather than passing through the quadrupole. Ions that make it out of the quadrupole will be detected by a detector, and you can figure out how much of a particular protein or lipid you had in your sample by figuring out how many ions of that protein or lipid made it to your detector. So this is likely not a 100% accurate description of a quadrupole, but yeah, hey, I'm still learning. Yeah, thank you.